Welcome to another mini-series. In this series, we're going to cover model assessment and counterfactual simulation. Up until now, we've mainly focused on how to specify the model and how to estimate it, and we covered a broad set of topics along these lines, talking about different ways that we can enrich a discrete choice model with preference heterogeneity or dynamics, and also different ways of estimating the model, whether it be by maximum likelihood or method of moments or some other type of estimator. But once we have our estimates, that's where the fun begins in terms of using the model for counterfactual prediction to discuss optimal policies. And because the model is used for these exercises, we need to make sure that the model is valid before proceeding. And in today's video, we'll talk about model fit, which is the first step or the lowest hurdle that a model would need to clear in order to be deemed valid for counterfactual analysis. Let's go through a few slides to showcase the topics that are most important. As we've talked about in the past, model fit consists of showing that our model can match the data. And the reason this is so important is, as I just said, counterfactuals rely only on the model, and so we need to make sure that we're certain that the model is good. But there's not really a set of metrics that everyone reports to validate their model or to show that their model is valid. It tends to be ad hoc because the model itself is quite unique from paper to paper, and so there's no standardized best way to show that the model is fitting. The most typical first stop in this process would be to show that you can recreate the outcome variables of your analysis using your model. In a discrete choice model, this would just be looking at, for example, the share of each alternative that's chosen by the decision makers. If it's a dynamic model, then maybe we would want to check certain choice transitions. If there's a continuous outcome, we could compare the average of those outcomes. And I wanted to go through a brief example of how one paper does this. This paper was published in 2022 in the journal Quantitative Economics, and it's looking at the role of school and crime among teenagers in Chile. The basis of the paper is wondering if we can make school better for troubled youth. Will that prevent them from committing crime? So really important policy question, because if you tend to develop habits that are criminal as a teenager, that might affect you for the rest of your life. So they come up with a dynamic discrete choice model where they are analyzing high schoolers' decisions to attend school, what type of school to attend, and what type of criminal activity they're engaging in. And the model fit table, this is just one excerpt from one of their tables that shows the model fit, just to illustrate what I was just talking about earlier in this video. They're comparing, using their model, what are the averages of these different variables, and then what are those same averages in the data. So if the model is useful, then we would hope that it would recreate arrest rates among youth, or the rates of people who are never arrested, or the grades that they earn in their classes, their likelihood of not dropping out, their overall education level. So as you can see, this paper is fitting well. It's published, so it went through the peer review process, and the reviewers and the editor deemed it to be a good enough model fit that we could trust the counterfactuals that they go through later. And their main counterfactuals are thinking about, what if we could commit some more government funding to improve schools? Would that reduce criminality among teenagers? And they find that it does. So that's the policy takeaway from the paper. So just broadly speaking, if we're using a structural model, we've estimated it. There's two main ways that we can produce these model fit statistics. So first, we can simulate data from the model. We take the model as reality, and we use the estimates of the parameters that we got from our estimation routine and any kind of initial conditions in the data, and then we simulate all of the outcomes. And if it's a dynamic model, then we're going to simulate throughout time. Another thing we could do is we could just take all the data and all of our parameters and do some kind of prediction function that would give us y hat, and then compare that with the actual y in the data. This is like x beta hat equals y hat in a linear regression model. So if we were to do option 1, what would that process look like? Well, we would have to first draw the unobservables from the model. And this gets back to the fact that we have to fully specify the model in order to run counterfactuals in most cases. And then we combine those unobservables with any initial conditions from the data. So especially if this is a dynamic model, we'd want to know like what was your endowment in period 0 before the model began. And then you take that endowment and whatever unobservables and the parameters, and then that would be like your first period outcome, and then maybe your second period outcome depends on your first period choice, and so on and so forth. And you kind of roll the model forward to get the full history of choices or whatever you're looking at. So in a dynamic model, typically the x's in the next period involve the y from the previous period. And so that's why we have to do this rolling forward kind of chaining across time. And if we've estimated the model using simulated method of moments, we should already have code that does this. And so this would just be basically evaluating that simulation function at the estimated parameter values. And then we would typically want to repeat this process several times to mitigate simulation error in our final presentation of the average y from our model. So that's option 1. And then option 2, we can just take our data, apply our estimates to it, get y hat. And so that's basically what we would do if we had a linear regression model, for example. And the main point here is that if our model has lots of latent variables, we're not going to be able to do this because we need to simulate those latent variables. That's the only way that we can see them for the purpose of producing outcome variables from our model. So these could be unobserved types if we're doing like a finite mixture model, or other unobservables that we can't see them in the data, and so we can't produce them using the data. We have to produce them using the model. So if this is the case, we really have to do option 1. We can't do option 2 for models like that. So that is a little bit about how we use our model to generate data to test if our model is reproducing key patterns in the data. Our next video will go a bit deeper on this topic and talk about how we can validate our model more formally. And this is a greater degree of proving that the model works so that we can have a greater amount of faith that the conclusions that the model implies would in fact be the truth if the model were the real world. Thanks for joining this video, and I'll see you in the next one.